So good afternoon, everybody. This is another in my Once Around series of talks, Once Around Barnard's star this time. Barnard's star is a small red star that lots of people have heard of despite its relative obscurity. And there's been a lot of mystery about it over the years. It tends to be commented a lot in various textbooks and so on. So let's just start off with showing you where it is. And it's in the almost unheard of constellation of Ophiuchus, which is the 13th constellation of the zodiac through which the planets pass, and the one that the astrologers all ignore, this one down here, underneath Hercules, so low in the south during the summer. And you can see marked on the map here with a little ring, this is the position of Barnard's star. And as I say, a very obscure star. It's only magnitude 9.5. The lowest magnitude that you can see with the naked eye is magnitude 6, and the brightest stars are first magnitude 1. Each step corresponds to a factor of 2.5 for historical reasons in the way it was set up and defined. And so this is 3.5 of those steps below visibility. It was discovered and is now named after Edward Emerson Barnard, pictured here with the business end of the 36-inch refractor at the Lick Observatory, the second largest lens-based refractor telescope ever built. The bit largest was the 40-inch at Yerkes near Chicago, but this one's on Mount Hamilton above the hills surrounding Silicon Valley, and I've had the privilege of going and visiting it a couple of times. It's a magnificent piece of equipment. So what's all the fuss about this magnitude 9.5 star? Well, Barnard noticed that it was changing its position, moving across the sky. It was doing this back in 1916. He took a series of photographs and realized that the position was changing, and doing so very quickly indeed. You can see a little animation on the screen there of the position of Barnard's star with the date beside it, going from 1985 to 2005 and back again. So 20-year period, moving in chunks across the sky there, pictured every 5 years. Well, Barnard measured it as moving 10.3 arc seconds every year, which doesn't sound like very much, but for a star in the sky that normally seem to be fixed, that's a lot, and it's a record holder still to this day. It's moving across our field of view from here on Earth faster than any other known star, and you can see it works at 1/4 of a degree in a human lifespan. So it's enough that you would notice it maybe if you were looking at it and mapping it with any reasonable duration of a series of observations. Now, the reason that stars like this one seem to move so quickly is either because they're moving very fast or because they're quite nearby. And in this case, it is clearly a nearby star. The distance was measured fairly straightforwardly using the parallax system. You take 2 lines of sight from opposing positions of the Earth in its orbit 6 months apart, and you will see that the position seems to change relative to the stars in the background. Now you can do that, work out the parallax angle, and with a simple bit of trigonometry, because you've now got a nice isosceles triangle, you know the angle and you know the base, so you can work out the height, and you come out with a distance of 6 light years roughly, and that makes it the second closest star to the sun, or the 4th closest if you count the Alpha Centauri system as being 3 stars, which I suppose we could, but it's the second closest system to the sun. In terms of human units, we can glibly talk about things like 6 light years as not very far, but I just wanted to illustrate it. It's each light year is 10 trillion kilometers, which is 6 trillion miles, and A trillion doesn't sound to mean very much to most people, I suspect. But if you drove on an interstellar highway that somebody had built to Barnard's star, and you managed to drive 30,000 miles every year, it would take you 200 million years to get there. And if your car's engine was super reliable and managed 1,000,000 miles before each engine replacement, you'd get through 6 million engines. So it's a ridiculously long distance. The fastest spacecraft ever launched, I worked out, would take 175,000 years to get there. So even traveling at the sort of speeds of things like Voyager and New Horizons out into the interstellar realm now, you're still going to take hundreds of thousands of years to cover the distance. Here's a little map of the local area with the sun in the middle. We've talked on previous occasions about the Oort cloud, which is really the limit of the extent of the influence of the sun and the cometary bodies that orbit round it. That's around about 1 light year. 2 light years, 4 light years, you're still just about to get to Proxima Centauri at 4.24 and the rest of the Alpha Centauri system over there. But Barnard's star over here, 6 light years, comes second. Just beyond that distance, we do get a few more objects. We've got these two here with their WISE numbers. These are brown dwarfs, so they're smaller even than red dwarf stars, and they're failed stars. They're not massive enough to begin their nuclear fusion. And there's another one over here in the sort of 6 to 8 light year bracket. So there are a few of these others, but we've not discovered anything closer than Barnard's star since 1916 and Proxima Centauri in 1917, in fact, 1 year later. Now, of course, this is not a static thing because all the stars are making their own orbits around the galaxy. And at the moment, it so happens that on this chart, we are here on the dotted blue line, and Proxima Centauri in the Alpha Centauri system is the nearest star to us, followed by the Alpha and Alpha 1 and Alpha 2 stars. And then Barnard's star is the second closest out here. But as you can see, Barnard's star is approaching us quite fast. We can look at the spectrum of the light, measure the amount of shift in the emission and absorption lines in the spectrum, and we see quite a big blue shift overall, which is telling us it's coming towards us at 110 kilometers per second. And if we run that forward and extrapolate, we see that in 11,000 years' time, Barnard's star is going to become just 3.75 light years from us, and then it's going to start receding again. But it still won't overtake Proxima as the record holder, because Proxima is also approaching us slightly more slowly, and it doesn't quite catch up. You can see some of the others that are going to swing past near approaches to the sun, and you can see that Alpha Centauri is going to start receding from us. And in fact, Proxima is in orbit round the Alpha Centauri system, and will switch places and become further away than the other two, around about where the mouse pointer is here, in 25,000 years' time. And a star called Ross 248 eventually takes over for a short while as being the nearest. Now, even when Barnard's star does get to 3.75 light years from us, you still won't be able to see it. It's going to be magnitude 8.5 then, so 1 magnitude brighter, but still more than 2 magnitudes fainter than will be visible with the naked eye. So we're just not going to see any of these except for Alpha Centauri, which is a much more powerful bright star like the sun. Barnard's star itself, though, it's an M4 class red dwarf star. That's a medium-sized red dwarf. Temperature 3100 Kelvin, so quite a lot cooler than the sun. You can see the temperature of the sun there. And just 14% of the sun's mass. The minimum for a red dwarf to undergo any nuclear fusion in its core at all is 7.5% of the mass of the sun. So it's double that minimum mass, so there's no danger of it failing and being a brown dwarf. But it's very, very much fainter, 1/2500th of the mass, of the luminosity of the sun. Rotates in 130 days on its axis. We can see that, but again, spectroscopically, we can look at the rotation, and we can also note that quite a few active stellar flares on it. Although it seems to have gone quiet since 2005, and it's perhaps having a period rather like the Maunder minimum on the sun, where there were no sunspots for about 100 years. It seems to have gone very, very quiet indeed. It's very noticeable that the smaller these stars are, the longer they take to rotate. You can compare 130 days here with the 26 days that the sun takes. And just to give you a sense of scale visually, here's the sun in just a quarter of it, compared to Barnard's star and the planet Jupiter. You can see Barnard's star is a little bigger than Jupiter, but a lot smaller than the sun in terms of radius. Now we have its position on the very famous Hertzsprung-Russell diagram that classifies stars according to brightness and temperature. And you can see here is Barnard's star down here, and it's a red dwarf in this tail of the main sequence here, burning hydrogen, converting it to helium in its core. And the hotter the stars get, the more massive they are, the hotter they are, and the faster they burn their fuel, till you get to the sun up here as a yellow dwarf star. So we've gone through the orange coloured stars to the yellow ones, and then on up the main sequence through the white stars and up to the blue stars right at the top here, the real monsters, the powerhouses. The ones at the top right are the aging giants, where they've run out of hydrogen to burn to helium in the core and have gone on to using other nuclear fusion processes to power themselves. But Barnard's star will never do that. It will never really get much beyond the size it is now. These little tiny red dwarfs, we think that they die in a different way. In fact, though, no red dwarf star has ever died, because their lifetime is around about 1 trillion years, and that's 1,000 billion, which is a lot longer than the current age of the universe, which is only 13.8 billion. The reason being, they run very, very slowly and efficiently at a low temperature, burning their hydrogen very slowly, and they burn all of it. They have a fully convective core and a fully convective outer layer that mixes all the material in the star. So all of their mass is available to them for the process of fusion. That's not the case with larger stars like the sun, where the outer layers don't efficiently mix with the core at all. And so the sun, it will only use about 1/10 of its available fuel before it swells up into a red giant and goes on its other evolutionary processes to its eventual death. We think that eventually this will use up all of its hydrogen and become a ball of helium. It doesn't have the mass to create the pressure and temperature to start burning the helium at all, and so it'll just end its days cooling down as a helium white dwarf. Just as an illustration of how common red dwarf stars are, this is an estimated chart of the abundance of different types of stars by temperature and color. So you can see the vast majority, over 3/4 of all stars, are red dwarfs. Then there's another 12% in the orange K-type stars before we get to the orangey yellow ones like the Sun, just 7.6%. The ones slightly hotter than the Sun, the F-type stars, 3%, and hardly any of the white and blue stars. Now this is a double whammy really. Firstly, nature finds it much easier to build a small star than a big one, so a lot more small stars are formed than large ones. It's just so much easier to get all the material together. Secondly, because they live such long lives, they stick around, in the case of red dwarfs, essentially forever. Whereas the other stars go through their life and disappear, and the larger they are, the more rapidly they do so. So the O-type stars only live for 1 million years, so the total population of them is constantly being regenerated and then disappearing and needing to be regenerated again. So at any given instant, a snapshot in time, you just see the current set of O-type stars, as opposed to the red dwarfs, which are all the red dwarfs which have ever been formed. So Barnard's star has always been the subject of mystery because of the possibility of detecting planets around it. Now, as I've said, it is a very old star. It's estimated somewhere in the range 8 to 12 billion years old, and it doesn't have very much by the way of elements beyond helium in it. It won't form any. It was only therefore going to have within itself the carbon, the oxygen and the metals and so on that were around at the time it formed. And those get built in large stars that explode as supernovae and distribute their contents around to form new generations of stars. As we were just saying, they live fast and die young, but they make heavy elements in the process. But Barnard's star, being so old, is stuck with a heavier element content that was around back in the day 8 to 12 billion years ago, and the chance of having any rocky planets with metal cores like the Earth seems somewhat diminished, because the planets will have been formed out of the same cloud of material that formed the star. And so if there are any, they're reasonably likely to be gas giants made of hydrogen and helium rather than necessarily rocky. It's not out of the question that there could be enough material there to form a few small rocky planets, or at least planetary cores, but it's always been a bit of a question, and it very much depends on whether Barnard's star is 8 or 12 billion years old, because the difference would have made a lot of opportunity for more of the heavier elements to be present in the original nebula. But back in the 1960s, a Dutch astronomer called Peter van der Kamp was very famous for studying Barnard's star and tracking its proper motion across the sky, looking to see if he could detect any sideways movement as well as the linear movement of it. And he claimed that he had, and he attributed this to the discovery of at least one, and in fact later 2, planets orbiting around Barnard's star. The idea being that a planet orbiting a star is pulled into the orbit by the mass of the star, but the planet pulls back and causes the star to wobble around in a little tiny orbit all of its own, in a little tiny circle. Often that circle is smaller than the size of the star, but nevertheless, if you had a particularly small star and a large planet, then it might be enough to deflect the path of the star across the sky such that we could measure it. That was Peter's idea. And indeed, he chose wisely, because Barnard star is a very low mass star with very apparent proper motion, so it was a good candidate to try, because with a low mass star you don't need such a large planet to make a noticeable effect. His initial suggestion from his data was that he'd found a planet 1.6 times the mass of Jupiter orbiting at 4.4 astronomical units. So that's very much in a almost Jupiter-like orbit. And such a large planet would indeed be plausible as causing a noticeable wobble, perhaps, in the movement of the star. Later on, he revised it to 2 planets, one of 1.1 Jupiter masses and one at 0.8 Jupiter masses. And his data that he was going on was his tracking of the position from 1950 to 1980 or 1975 of his measurements of the position in both the celestial longitude, the right ascension coordinate, and the celestial latitude, declination coordinate. And you can see his marked little circles there going along in time, and with the 5-year intervals marked. And if indeed there was a planet there, you would expect it to cause the star to move backwards and forwards in a sinusoidal pattern as viewed from the direction of the Earth. And that looks very much like what we've got here, with an 11-year period or thereabouts, the 11 years between the peaks and troughs in the graph. Unfortunately for Peter, nobody else could ever reproduce his findings. It would have been the first detection of a planet around another star if it had been confirmed, but try as they might, other astronomers could not reproduce this. And eventually, after Peter's death, the successor who took over his observatory from him went and reanalyzed all of the records and the data and realized that actually what you have is data that fits a straight line movement of the star up to that point there shown, and another straight line there, and a third straight line here. And the reason for suspecting that this is what is going on is because in 1962, the telescope engineers came along and took the telescope to pieces to do maintenance and put it back together. And you know what I'm going to say, they came back 10 years later and did it again. And this created a misalignment each time in the telescope, which created the effect of changing the slope of the lines that Peter thought he was measuring. So this rather explained why he was getting the readings he was getting, and nobody else could find it. So I'm afraid that neither of Van der Kamp's planets were ever confirmed. But I'm happy to say that it made the news in 2018, and this is an extract from the BBC website, where planet Barnard B was confirmed. And it's not one of Van der Kamp's planets, I hasten to add, but it is a planet orbiting around Barnard's star. And at the time, that made it one of the closest planets that we know of, still second only to Proxima Centauri b, which was discovered just a few years before. And we estimated initially the mass was round about 3.2 times the mass of the Earth. So an interesting size of planet, slightly bigger than the Earth, but nowhere near the size of even the things like Jupiter or Saturn or even Neptune. So its orbit around the star was worked out, and it orbits around in 233 days at a distance of 0.4 astronomical units. 1 AU is the distance to the Earth, from our sun. So we've got the solar system by comparison at the top there with the inner planets, Mercury, Venus, Earth and Mars. And planet B, as it's called, rather unexciting name, orbits round Barnard's star roughly at the same distance that Mercury does from the sun. And it takes 233 days, which by coincidence is roughly how long Venus takes to orbit round the sun. So they shares characteristics with each of those in some sense. Now, of course, in terms of the environmental conditions on such a planet, it might be close in, but the star itself, you'll remember, is only putting out 1/2500th of the energy of our sun. So it's very, very dim and not much heat coming off it. If we actually look at the different types of stars, you can see how the amount of energy and the wavelength at which it's emitted changes according to the mass of the star. So these little tiny red dwarfs, this would be a very cool red dwarf indeed at 2300. The light curve for those goes, as in the orange here, into the red where we start to see it in the visible, already declining though through to the blue end, and then stops in the early part of the ultraviolet part of the spectrum, with the peak is in the infrared, whereas the sun has its peak right in the middle of the green. And it's no surprise that our eyes are sensitive to the region where the sun is brightest. It's a natural consequence of evolution. Also because the atmosphere happens to let those wavelengths through though. And the hotter stars, the peak moves even further to the left to higher energy and shorter wavelengths on this diagram. And so actually a lot of the energy coming from the star is in the form of heat, the infrared radiation. But we can calculate things about how much heat a planet will receive at different distances from various types of stars. And you can evaluate what's called the Goldilocks zone, or the habitable zone, where it's not too hot, not too cold, just right. And when we say just right, we mean just right for water to exist on the surface. So temperatures in the range 0 to 100 degrees centigrade. Now for a sun-like star, the habitable zone is arguably just beyond Venus to just about the orbit of Mars, with Earth nicely placed in the middle. It's too hot further in where Mercury is, and probably too hot where Venus is. For hotter stars still, that extends further out, and this hypothetical hotter star here would have Mars in its habitable zone if that was the distribution of planets around it. But for the cool red dwarf stars, obviously the habitable zone is further in. So the question really is Barnard B in the Goldilocks zone? Well, there's a rather technical plot of its orbit, and it's slightly elliptical. The Goldilocks zone is marked, and it goes from 0.05 astronomical units to 0.12 astronomical units, which is very close to the star indeed, due to this very, very low power output, 1/2500th of the power of the sun, remember. In fact, the snow line is marked at 0.15 of an AU. That's the point at which any planet would have a natural temperature below 0 degrees, and so water would be in the form frozen up as ice or snow, and indeed soon drops as you go further away to bringing things like ammonia, which has a melting point of minus 33 degrees centigrade. That would also soon turn to a liquid and indeed start snowing out. So Barnard B orbits actually well beyond the snow line and is in an elliptical orbit going from 0.27 to 0.53 of an astronomical unit. So 0.4 is the average. So it warms up a little bit as it comes in, and then goes out to much colder temperatures when it reaches its far point from the sun at half an AU. So it's not in the habitable Goldilocks zone itself, and they've classified it as a non-habitable planet for that reason. It's also, though, beyond the tidal lock limit. The moon is tidally locked to the Earth. It always keeps one face pointing towards us, and this happens with any object orbiting its primary within a certain radius. And the tidal lock radius for Barnard's star is just 1/4 of an AU. So Barnard B avoids that. Now, tidal lock is a little bit of a conundrum for planets, because they would get very hot on one side and freezing cold on the other, with maybe a temperate region in between. So it's not something that you really want to happen. And it's a problem for a lot of red dwarf stars. If we plot the habitable zone here for different types of star here, so for the smallest red dwarfs, the habitable zone is here, and it gradually gets further away as the star gets hotter, and the tidal lock distance is here. So actually most red dwarfs have their habitable zone inside the tidal lock radius, which is certainly going to make environmental conditions rather complicated, if not impossible. You probably get either too hot or too cold, unless you were managing to sit in some sort of temperate zone near the poles or something. The K-type stars, they're all right. They have their habitable zones outside the tidal lock radius, and K-type stars are a very good candidate for finding habitable planets for that reason. And the sun, well, the sun's a G-type up here, so not a problem. You can see Mercury's on the boundary of tidal lock, and it does indeed have a tidal lock relationship with the sun. It's a bit of a complicated one. But Barnard's planet B was discovered not by the method that Peter van der Kamp was using of looking at the movement of the star itself, but by the radial velocity method, which is to look for the change in the spectral line shift caused by the to and fro motion of the star as it goes round in its tiny little orbit, perturbed by the gravity of the unseen companion. And the light will be shifted towards the blue if the star is coming towards you, and into the red if it's moving away from you. And we can detect that change very, very much more accurately than you could ever hope to plot the position of the star on the sky. So it's a much more subtle technique. But it has an interesting drawback, which is that it only measures the movement along the line of sight caused by the companion planet. And by virtue of some mathematics here with the diagram shown on the right, if the orbit of the planet is tilted compared to the line of sight, so it's not orbiting in the same plane as our viewpoint towards the star is pointing, then we only see part of the movement. And the more tilted it is, the worse that gets. And this means that we underestimate the mass of the planet. So the mass that we give of 3.2 Earth masses is a minimum mass estimate, assuming the planet is in an orbit completely in the plane of the line of sight. The more tilted it is, the more of an underestimate that is going to be. And until we are able to find other methods for spotting the planet, working out the tilt, we're not going to be able to resolve that. So this means it could be a 3.2 Earth mass planet, or it could be considerably heavier. In fact, it could be up to about 12 Earth masses. And so there are two real possible candidates. It could be at the smaller end of that mass range, 3.2 to maybe 7 Earth masses. That would be classed as a super Earth. And at the distance it would be beyond the snow line, it would certainly have a lot of water and ammonia and other ices rained out and frozen out onto its surface, and be able to hold on to those against the radiation pressure from the sun, from the star rather, from Barnard's star, and have a very thick, steamy and watery envelope in general. At the higher end of the mass range, though, in the sort of 8 to 12 Earth masses, it would be more of a mini Neptune, because it would now have gravity strong enough to hang on to the even more volatile elements, hydrogen and helium, and there's a lot of that around. 3/4 of all the atoms in the universe are hydrogen and nearly 1/4 helium. So if you can hang on to those, then you certainly would soon form into a gas giant planet, or even a mini gas giant, as is the possibility here, a mini Neptune. So it very much depends on the tilt of the orbit from our point of view as to which of those is likely to be the right answer. But we can have some fun speculating. We know it's at least 3.2. So if we assume it's around about that, and that we're looking at the thing more or less edge on, then it would still be a super Earth planet. It would have stronger surface gravity, be about 1.5 times the pull of gravity standing on the surface there. And it certainly should hang on to a certain amount of atmosphere. Heat from the star itself would naturally give it a temperature, though, of minus 170 degrees centigrade. Very chilly indeed. But with a thick atmosphere held in place by stronger gravity, containing lots of things like carbon dioxide or methane or other molecules. In fact, carbon dioxide would probably be freezing out at this temperature, wouldn't it? But a thick atmosphere could nevertheless create a greenhouse effect that would boost that temperature up to a much more respectable level. The Earth's temperature is already boosted by something like 40 degrees just with our atmosphere. When we look at Venus, we find its temperature is boosted all the way up to 450 degrees C by its atmosphere. So it's entirely plausible that a thick atmosphere on a super Earth could bring that temperature up into the positive degrees Celsius region. And if so, it might have interesting potential for weird forms of alien life on it. If the temperature is a temperate one because of the thick atmosphere, you might see Barnard's star as a very faint red glow in the sky through the thick clouds. It would only be at best about as bright as 100 times our full moon. And people have done a lot of speculating and what if scenarios about this, and think that maybe, you know, you might have some sort of weird vegetation here which is picking up the red light only, and the plants might be completely black in order to try and absorb as much energy coming from the star as possible to keep themselves warm and to grab all those photons for photosynthesis purposes, etc. But of course, this is all highly speculative. Now, another factor in favor of it, though, is geothermal heating. If you have a large planet, a super Earth, then you probably trapped a lot more heat in the center during the formation process. You've gathered together 3.5 times the mass. You've therefore gathered together 3.5 times the amount of heat in the core, either from the heat of formation of the planet, from the accretion process, or from the radioactive elements that you will have trapped. And so if you do have a rocky planet, it will have kept a very large amount of that heat within itself. And because larger objects have more volume compared to their surface area than small ones do, they leak the heat to space more slowly. And so even though this planet might be 8 to 12 billion years old, it would still probably have enough heat to have volcanic activity filling the atmosphere with all those greenhouse gases, and also a liquid core, which would, if the planet was spinning on its axis at a reasonable speed, which it probably is because it's not tidally locked to the star, so that's where the tidal locking factor comes in again, then you probably have a very powerful magnetic field, and that would be sufficient to protect the atmosphere from the direct effects of the solar wind coming from Barnard's star. And so the atmosphere would probably survive. That's very much the case as the Earth's atmosphere is protected here from the worst effects of the solar wind. Another possibility is that being a warmer environment like that, it might have enormous amounts of liquid water on the surface, having floated up to the top over its rocky core, and it might be like a giant version of Jupiter's moon Europa, with a rocky core, with a metallic inner core, probably molten, volcanic activity bringing that heat into the surface, but dumping it not out into the atmosphere directly, but into a liquid ocean that might be 100 or 1,000 kilometers deep, and that might take it well up to high altitudes, where it would then perhaps be covered in an ice layer at the outer surface, depending upon what atmosphere it had above it. So there are lots and lots of possibilities for this, and in coming years we're hopefully going to be able to start to answer some of these questions. That's not the only planet that has been hinted at, though. Barnards C has also featured in the recent papers, being suggested as orbiting further out than Barnard B, an even further, more frigid world. We're not certain of its existence. We're more than 99% certain of Barnard B, but Barnard C at the moment remains a wobble in the data and hasn't yet been confirmed. But what we do know from other studies is that we can rule out various possibilities. There are no planets that are 8/10 the mass of Jupiter or bigger, that we can say there's a maximum mass for any planets. And we've also been able to rule out any planets that are roughly Earth-sized in the habitable zone. Anything more than about 70% of the mass of the Earth we would have already detected if it was that close in, because it would cause a larger and more frequent wobbling, which we would be able to find. So there are planets around Barnard's star, probably at least 2, but maybe there aren't very many deep inside in the inner reaches, or if they are, they're likely to be very small ones. And that fits with the potential lack of rocky material to build the planets out of. So maybe these are indeed mini Neptunes. One way that we might find out is that later on this year, the James Webb Space Telescope is going to be launched in October, and one of its first science goals is to directly image the system and look to see if it can directly take photographs of Barnard B. And if it can, then we should also be able to do spectroscopy on it and start to learn about the composition of the atmosphere. We'll also get an estimate of the size of it, and therefore be able to start to make more intelligent guesses about the mass, and if we can track the orbit in 3 dimensions, then we can solve the mass exactly. Now, another aspect that's always been speculated about with Barnard's star is as a destination candidate for an interstellar mission. And in particular, you may remember the Daedalus proposal, which was to send a spacecraft out all the way to Barnard's star. And the idea would be to use nuclear power to accelerate the spacecraft to very high speeds. Over a period of 4 years, it would achieve 12% of the speed of light. And by doing so, it would be able to fly to Barnard's star in just 50 years. Absolutely enormous spacecraft compared to the Saturn V here. And the proposal is not to build it on the Earth and launch it. That would just not be feasible, but to build it in sections and probably build it out in the asteroid belt, or possibly in Earth orbit, but more likely to mine the materials from asteroids and build it in that region from the raw materials that are available there. Otherwise, we'll be perpetually carrying fuel everywhere to take things to and from it. Here's a diagram of the idea. It's a two-stage unit, both powered by nuclear power. They have propellant tanks, and then they eject small elements of nuclear fuel into the bell-shaped reaction chamber at the back and ignite it using lasers or electron beams to trigger the nuclear fusion process and accelerate the thing forward. And then, of course, once the large tanks on the first stage there are exhausted, they'll ditch that bit and fly the second part across, accelerating even further. Right at the nose of the spacecraft, you can see a beryllium disk. This is because if you're traveling at 12% the speed of light, even crashing into the thin interstellar gas is going to be quite a dangerous process. And so this is an armored disc on the front there to try to take the hit of driving through that gas at enormous speed. This is how the engine would work. We've got the fuel is not heavy elements like uranium, but it's going to use fusion power and fuse hydrogen, which is injected from the front, forced into being a plasma by electron beams and contained by the magnetic field. So very much like the fusion reactor that we're trying to build on the Earth, but in this case, we don't have to contain the fuel forever. What we actually want to do is get it very, very hot and then have it fly out the nozzle at the back at enormous speed. The rocket equation that governs how all rocket engines work, no matter what the fuel, is that the exhaust velocity of your gas is everything. The faster the material comes out the back, the more you can accelerate. And it doesn't matter what it's made of or how massive it is, really. And so such an engine can achieve very, very efficient use of fuel, and is really the only way that we're going to get a rocket engine to reach those sorts of speeds. Now, if you were to be able to travel all the way out to Barnard's star and turn around and have a look back, this is part of the sky map that you would be able to draw. And the difference is minimal. We see the familiar things like Orion with Orion's belt here, Sirius, bright star, Procyon, the twins of Gemini, and so forth. But there would be one extra bright star in Orion, and that would be the Sun as a first magnitude star, just shining back at us. All the other stars would seem to have hardly moved. The nearest other stars to Barnard's star are, of course, Alpha Centauri and the Sun, and the other red dwarf star that was on one of the charts earlier, Ross 154. So very much has the same perspective on things, looking from Barnard's star as we would do. So I wonder, will we ever manage to get enough material and organization together to build such a giant probe and send it there? Or will it be things like the Breakthrough Starshot project, which plans to use laser beams sent from the Earth to accelerate small spacecraft with microelectronics on them that are propelled by the impact of the laser beam on a light sail, and to send those out in swarms out to destinations such as Alpha Centauri and Barnard's star. And again, they could possibly report back in a few tens of years even, because they could accelerate to half the speed of light with that technology. Well, I don't know. And just to wrap up, we've got a few minutes left, I thought I'd add a little bit about a newly discovered red dwarf star that may turn out to become quite famous. Only discovered in 2003 and had a very large proper motion. Again, 5 arc seconds. That's in the top 10 of stars for their proper motion across the sky, half the value of Barnard's star. And indeed, it's twice as far away, 12 light years. That makes it very, very dim and very hard to observe at magnitude 15. So you need a very large telescope to be able to see it. But what's interesting about Teegarden's star is that just in 2019, scientists have announced the discovery of 2 Earth mass planets. And these really are Earth mass ones. Teegarden B orbits inside what's described as the optimistic habitable zone. So the equivalent in the solar system would be somewhere between Venus, which is too hot, and Earth, which is just right. So it's a little bit on the toasty side. And Teegarden C orbits on the outer edge of what's described as the conservative habitable zone. That's the slightly too cold region, similar to Mars. So we've got one that's too hot and one that's too cold, but none that are just right. However, we probably haven't found them all yet. There may be others yet to discover. And so the search for all of these planets around these red dwarf stars continues, and we do seem to be finding more and more of them the more we look, which is interesting because 10 years ago there was quite a lot of doubt about whether red dwarf stars would have any planets at all, and certainly if they did, that they would only be tiny little asteroid-like things rather than planets of the order of the mass of the Earth. They just felt that these stars wouldn't have enough mass in their protostellar disks to form families of planets, and that's turning out very much to be not true. So a very interesting development. And I will bring it to a close there. Thank you very much for listening. I hope you enjoyed that trip to Barnard's star and back, even if we can't quite go there for real.